All right, so I was just saying that on homework G3, as just pointed out to me that on part 2 of that homework, it originally had said in bold that you're supposed to detect 9 requests or more. So that's kind of the critical effect, critical number that you want to detect in your t-test. But then later on in the text, it refers to detecting 2. And the right number there was 9. In a previous iteration of the homework assignment, it was 2, but when I changed it for this go around, I changed it in one place, but then didn't notice I'd had a couple more downstream. So apologize for that confusion. I have gone ahead and updated it on the Canvas site, and I'll try to post an announcement as well pointing out that. So go with the bold number if you've downloaded the old one. If you look at the new one, it all should be consistent. So you should do your power analysis looking for 9 on part 2 of that homework G3. All right, and then so just other announcements this week where you've now moved into looking at the output analyzer in lab 9. So you went for input 2 weeks ago, and now we're looking at the output analyzer. So a lot of the cool statistical tests we've been talking about have been built for you in the output analyzer. It's not the cleanest of tools. Arena sometimes does not put them, the Rockwell hasn't put a lot of polish on these things, but still it can be a lot quicker if you're not accustomed to using other tools. So if you need to do something like an ANOVA or a t-test, calculate a confidence interval, the output analyzer allows you to do that. And there's some additional interesting tools like OptQuest that allow you to do even more. And we'll talk about those very briefly towards the end of this lecture. And then in lab 10, we go into some advanced topics in modeling that we haven't covered so far. So like batching, for example. So if you go back and think, well, how could I build the muffin simulator in Arena so that it creates batches dynamically and breaks them apart and puts them back together, then you'll learn about how to do things like batching in lab 10. So then after that, there's no other labs, and so you can view that additional time there as help for your final project and building your final projects. And so either if that means seeking out additional help from me or the TA, or just working on your own and using that time that would normally be for lab and working on your projects. So the input modeling reporter was originally due Sunday, and I guess it technically still was due the previous Sunday, but I've extended the availability date to this upcoming Sunday. And as I've been getting them, I've been trying to give you that feedback. And so I've returned at least a little bit of feedback, but I've seen more trickle in since Sunday, and so I'll work on getting those back to you. And if I manage to get you feedback back, and there's still availability window, if you feel like you'd like to make some amendments to that and re-upload a new one and get new feedback, that's fine, just so long as it's before the new availability date, which is this upcoming Sunday. So then after that, I basically leave you alone. Don't bother you with the final project anymore until the final week of classes, where you submit your presentation video and final report to Canvas. And then you will then peer review one presentation and one final report from your peers, from your other classmates, and then you'll submit your peer review for the presentation and your peer review for your final report the Saturday before finals week. And then because, and by finals week here, I'm referring to the original finals week, which is now innovation week. And as I've already mentioned to you for the actual final exam, instead of having a final exam pre-take and a retake, we're going to do a two-stage final where you'll take a final by yourself on the Thursday of the last week of classes, and then on the Friday of last week of classes, then you basically get that same exam again, but you get it open notes without lockdown browser and with the ability to collaborate with your peers, so with other people in the class. And that second one will be 20% of your final exam score, and the first one will be 80% of your final exam score. So it's first time I've tried one of these two-stage exams, but it seems like this, because they've forced us to shove all our finals in the same week as the last week of curriculum, it seems like a great time to try it. So that's what we're gonna do. And so other activities, Canvas activity J3 will be due in 1 week. This is lecture J1, so this will be due a week from today. Homework G3, I mentioned that in question 2, there's a power analysis problem, and that one, the number should be 9 is what you're looking for, not 2. So trust the bold text to 9, and again, I've already uploaded a corrected one that has, not only has the bold 9, but also any numbers after it also refer to that same number. So you're looking for a difference of 9. And if you do it right, then you should sort of get a nice clean power analysis. I don't know how the power analysis would have come out with 2, but my guess is when you're staring at those operating characteristic curves, it would have been harder to figure out what the right sample size is. But if you use 9, it should be pretty easy to figure out what the right sample size should be. Okay. Let's see, anything else? Is there any questions? Okay. The ICAs are always due before the lecture that they're named after. Okay. So we have been talking about hypothesis testing a lot, so that we're trying to get into the type 1, type 2 error rates and so on. Trying to get a better kind of conceptual feel for it. Election day is a great time for that, as I kind of mentioned in the share from those of you who are coming in a little bit early. When you have small effect sizes, that corresponds to when the null hypothesis in an election is that the 2 candidates are equal, and an election is actually trying to find a difference between them. And if the difference between them is very, very small, we know that hypothesis testing can find that difference, but the only way it can find that difference, to have the statistical power, the sensitivity to find that difference, is if you have lots and lots and lots of samples, which is why you ask people to vote, especially when there are very small differences between the candidates. In order to detect those differences, then you ask them to vote. Now, you say, well, but an election really isn't a hypothesis test. There's no analysis of variance. And if you did say that, I would 100% agree with you. And that, the way a statistician would run an election is you'd actually run something like a t-test. You'd actually run something where you would take into account the variance. You'd say that, we have a confidence interval on, we can say that, well, 51% of the country thinks this, but there's actually a confidence interval where that 51%, it's actually got some bounds where we're not quite sure it's 51%. The real population could go all the way down to 48, and the other part of the population could go all the way down to 54. And so given those confidence intervals, which is what we're going to start introducing today, then that actually tells us, well, maybe we can't make a decision. Maybe we haven't actually detected where maybe the effect is so small, we haven't taken enough samples, in which case we need, to maybe have another election, or that. So other countries have, and actually there's some small communities that have this thing called a single transferable vote, where if your candidate can't possibly win, then you have ranked candidates and your second choices now get tossed into a new calculation. So there's many, many rounds of, as candidates get eliminated, then the people who voted for them, their next choices in their ranked list end up getting tossed in. And that has the effect of amplifying the effect between candidates, so that with the amount of voters you have, you can start detecting these things. So that's one way that you can solve these sorts of problems, or you can run another election or something like that. But so that's kind of how we would do it if we were designing an experiment. Of course, politics doesn't run in the most kind of scientifically sound way all the time, but the basic heuristic of trying to get people to vote is just a heuristic of trying to increase statistical power, trying to increase the sensitivity of the process. When there's not much of when there's a huge difference between the candidates, you maybe don't need as many people voting, because the effect is so large that with very few samples you can get it. But when there's a small effect size, you need a lot of people voting. And so over time, I'm hoping as you come out of this class, you can start looking at things like elections, like the World Series, or whatever your favorite sporting tournament is, and start asking these type 1 and type 2 error type questions. And I hope when you look at things like the World Series, you can see that in 7 games, it's impossible for a binomial test to determine which team is better in 7 games. It's impossible. So statistically, if we were going to run the World Series again, we probably need more like 15 games to actually be able to tell the difference between 2 teams that are closely matched. Nobody would want to watch 15 games of baseball in a sequence. It's just too boring of a sport. So that's why we're limited to 7. Why not 1? Because you can make a lot more money getting people to watch 7 than 1. So 7 games, statistically speaking, is identical to 1 game. It's just as much noise. But 15 games is too much to ask from people. So for marketing reasons, we play 7 games because we just get a lot more money out of people in watching the sports, even though we're not getting any more statistical certainty out of the results. So those are the types of things that I'm hoping you'll start seeing as you start designing your own experiments and looking at data yourself. All right, so conventionally, the significance level that we're gonna, that we generally aim for is about 5%, and our type 2 error rate, we want about 20%, which means that our statistical power needs to be at least 80%. That's just the convention typically used in science and in this class. If you go into different fields, you might find that they have different conventions here, but these are the bright lines that we work with. 5% type 1 error, 20% type 2 error, which corresponds to an 80% statistical power. So last time we talked about the t-test, we talked about how this was invented effectively by an industrial engineer working for Guinness, who wanted to make it so that they could make inferences using less data. That's the whole point of these fancy statistical methods, is how can we confidently make an inference while not having to spend a lot of money or a lot of resources on running giant experiments. Before the t-test, stats was really an agricultural thing where you had fields, giant fields, where you effectively could run giant experiments, kind of like an election, and you could just use point statistics. Today, we're going to move to interval statistics, or start moving towards interval statistics, so that we can start capturing that variance, which is really important when you're only running 100 replications of your simulation and not 1,000,000 replications. So the key thing I wanted you to remember with your t-test is you can only apply a t-test if the samples you've taken are independent, and we'll talk about how we get independence in a simulation today, and from a normal distribution. And we'll talk about how in many cases, the things we measure from simulations are going to be coming from a normal distribution. Under those 2 cases of when they're independent and under normal distribution, then we make a hypothesis about the mean of that distribution. And so we have a hypothetical mean, which we can say, we think this simulation, or we're testing to see if this simulation output is different from a mean of 6. Now we're taking for granted the simulation output is normally distributed. And so now we're saying, given that it's normally distributed, that we're taking that for granted, given the data we've gotten out of the sim, we're going to use the t-test to see if these data are consistent with the hypothesis that the sim is representing an average of 6. And then our t-test helps us tell if the sim is or is not representing an average of 6. And so we mentioned that the way the t-test comes from this t statistic, which is effectively meant to generalize a z-score. You learned about z-scores in 380, where you have a statistical distribution, which is distributed by that you can basically wrap up into a standard normal after you kind of standardize it. Standardizing means subtracting the average and dividing by the standard deviation. So you standardized a particular statistic, and if you're lucky, it's normally distributed. And so standardizing it means that the null hypothesis will have a distribution which looks like a standard normal. But if you have very, very few samples and you're creating a mean, then the distribution of your sample mean won't be a standard normal. It'll be this other ugly thing we call a t distribution. And it just so happens that as you get more and more samples going into your sample mean, then the distribution of your sample mean goes from a t distribution, this thing that's low here and high on the tails, and it raises up and becomes a standard normal. So again, a t-test is just meant to be a generalized z-test. It's meant to be a way to generalize a standard normal. And to show you an example of what goes on inside a t-test is I've gone in MATLAB and I've drawn a standard normal here. Where I've actually drawn a t distribution under some null hypothesis. And so if my hypothesis were true, the data that I would get out from that true hypothesis, when I then ran them through the t statistic, would fall along this blue curve here. This would be the distribution of statistics I would get out under the case where my null hypothesis is true. So the simulation, if my simulation truly had a mean of 6, then it would produce a t-statistic values that every time I ran the sim, I would get a new sample mean. And those sample means would end up falling along this blue distribution here. Now, if I instead ran a sim whose mean wasn't 6, it was 8, its real mean inside the sim was 8, and then ran those sims over and over again and took sample means, then those sample means would fall along this red distribution here. And so I can see here that sometimes my new simulation that has the higher mean generates data way out here. It generates a sample mean of 5. And a sample mean of 5, or sample t-statistic of 5, that would very, very rarely happen under the true hypothesis, but it could happen under this alternative. But sometimes it generates, say, a t-statistic of 0, and a t-statistic of 0 is very common under the null hypothesis over here. So that's kind of the problem, is that even though there is a real effect between our two simulations, a difference in performance, for example, of 2 in the mean, then the t-statistics that are calculated still have an overlap. So what do we do for that? Well, one thing we can do, and so notice in the title here, I say this is from 4 samples of both simulations. And I'm assuming that the simulation data produce a standard deviation in both simulations of 2. So one thing I can do to reduce my ambiguity is take more samples. So if I do 20 samples of one simulation and then 20 samples of the other simulation, and then recalculate my t-statistics, then these are the expected distributions. So for my null hypothesis, it's this one over here, looks pretty much the same, right? If I go back, it looks, it might got a little more normal-like, so the tails came down and the top went up, but still located in the same spot. But the red distribution has moved over a little bit, and it itself has also gotten a little peakier. So if I were to go back, I see that the red distribution is sitting right next to the blue distribution. And when I go to the 20 sample case, the red distribution has been moved over. So by taking more samples, the same alternative hypothesis, when you calculate the t-statistic, the distribution of that t-statistic gets farther away from the distribution of the t-statistic under the null hypothesis. And if I do that even more, it gets even farther away. And as so you see, as I'm taking more and more samples, I'm reducing the overlap between these. So if I were to go back to that little diagram that we started with here, if I reduce the overlap between these, then what I'm going to do is I am going to get better error rates. And so I am going to reduce the chance of making a false positive or a false negative. So that's what we're doing by taking these additional samples. Now there's one other thing that I can do to increase my, my statistical power. And basically, and remember, this is assuming an effect size of 2. So what this is doing is that it's allowing me to detect smaller effects. By taking more samples, I can detect smaller effects. So 2 might have been so small of an effect that with 4 samples, I can't tell the difference. But with 30 samples, I can tell the difference when there's only an effect of 2. So that's, again, like the voting example. If you get more voters, you can actually tell the difference in the means population. So you can actually tell that there is a favoring of one candidate over another. If you get more samples, you can actually detect this too and be confident that you've actually detected a real difference. Now, the other thing that I can do, or I can hope for to gain statistical power, is if I can't take more samples, what I can do is try to reduce the variance of my simulation. How do you do that? You can say, well, I can just hope that I'm going to have a less variable system. Or there are tricks that we can do in design of experiments that remove other sources of variance. So, there are tricks like if I'm trying to tell the difference between whether an orthopedic shoe or a running shoe is better for, I don't know, the health of the knees over time. I could recruit 30 people to wear the orthopedic shoe and 30 people to wear the running shoe. But the problem with that is the random 30 people that I've generated are going to have natural differences from the other 30 people. And so it might just be that I get part of the variance, part of the difference I see between the running shoes and the orthopedic shoes is just the difference in populations. I might have accidentally chosen a healthier group of people for one group that testing the shoes. So what can I do? Well, with shoes, what's great about shoes is that everybody has 2 feet. I could put an orthopedic shoe on a randomly assigned foot of every person and put the running shoe on the other foot. And then if I now have my 30 or 60 people, I can compare for each person the difference between the 2 shoes. And that removes a source of variance, because now the difference in my 2 populations is not showing up in my data. So that's one example of how we can design an experiment to reduce variance so that we don't have to use as many samples. And so that's kind of where we're going in this section of the course. All right, are there questions about that, about this general idea of, want people to kind of be comfortable with these overlapping bell curve plots? Okay. Great, all right. All right, so far I've told you about that the t-test is test hypotheses on parameters. It's only a hypothesis on the mean of an assumed normal distribution. You cannot apply a t-test if the data you get out of an experiment do not look normally distributed, because you have to assume they're normally distributed before you can even start with the t-test. So with that in mind, the t-test is a very narrowly scoped hypothesis test. It's a type of a hypothesis we refer to as a parametric test. So the word parametric is one that I want you to kind of, become more familiar with, and that it is a hypothesis test where the hypothesis is on parameters of assumed distributions. So you get more power, more statistical power. You can detect smaller differences with fewer samples if you can assume that the data you have a particular distribution. And if you can't assume that, then go forth and use your parametric test. A t-test is a parametric test. And then you will be able to get more bang for your buck. But if you look at your data and they aren't normally distributed, you cannot use a parametric t-test. So then you say, well, what do I do, Dr. Pavlic? What do I do, Ted? How, if all I've learned is how to use a t-test. I need to compare 2 means. What do I do? In that case, I'll tell you what to do in a second here, but I won't give you a lot of details, but you'll forget. But then later on in life, when you actually need to use one of these, if you Google for non-parametric t-test, just Google for it. I can tell you in this day and age that Google is a tool that you will have available, or some search engine. If you search for non-parametric t-test, it will come up with things, you'll end up seeing things like the Mann-Whitney U-test. So there are standard things that over time you'll memorize, but initially, as long as you know what to look for, you're going to be able to find them. So by now, after 380, 385 in this class, you'll know t-tests. And I'm hoping after this class, you'll know that t-tests are parametric. So that when you're on a job somewhere and somebody gives you 2 data sets and says, is there a difference between these 2 data sets? When you do histograms of those data sets and QQ plots, and you say, wow, these aren't normally distributed, and there's no way you can make them normally distributed, I'm hoping that some of you out there will then go forth and say, I remember that there is a way to handle this situation. And you'll just search for non-parametric t-tests. And what you'll find is something like the Mann-Whitney U-test. And a U-test is a test on medians. Are the 2 medians of these populations different? But it does not require any assumptions of the distribution. You lose power when you go to the U-test, but it's universally applicable. So that's the reason we don't use the U-test everywhere, because when we can, we gain statistical power of the t-test. But if you can't use a t-test, a U-test is usually something pretty good to use. And you can use it on a wide range of data sets. It can be count data, it can be continuous data, discrete data. It is the only thing it's kind of bad for is when you have a lot of ties between your data. So you have a lot of data that comes out, but there's a lot of kind of overlap where you get the exact same samples in the two populations, like in the case of two discrete ones. But that's kind of getting into advanced stuff. For now, the reason I'm spending so much time on this, I just wanted you to burn into your brain that a t-test is parametric, but if you need a t-test for something that is not normally distributed, just look for a non-parametric t-test and you'll find a u-test. And then likewise, other things that we've learned about, the paired difference t-test. Well, there is a Wilcoxon signed rank test. How the heck are you gonna remember Wilcoxon signed rank test? Initially, you won't. You will come out of this class and I guarantee most of you will not remember the signed rank test, but you'll remember the paired difference t-test. And if you search for non-parametric paired t-test, you will find the Wilcoxon signed rank test. Likewise, you might remember ANOVA from 380, 385. ANOVA also requires normally distributed populations with same variance normally, but then you can generalize that a bit. If you search for non-parametric ANOVA, you'll find the Kruskal-Wallis test. In fact, some people call it the Kruskal-Wallis ANOVA or the KW. And so these are all tests that I want you to know exist. I don't think you need to know their names right now, but over time they will become burned into your memory because you'll Google for non-parametric versions of these and they'll just keep coming up. So that's kind of how you learn statistics in a modern age, is through Google. There are other terms that you might want to learn, like exact. So an exact test is one where you have met all of the assumptions. So an exact parametric test is the kind of proper application of a parametric test when the assumptions are met. So an exact t-test is when you absolutely positively know that this population is normally distributed. Then you absolutely know that your t-test is exact. Now in a non-parametric, an exact non-parametric method is a method that has no assumptions whatsoever. So for example, the chi-squared test, we would not call an exact test because we assume that that we have an expected number of counts in every bin that's 5 or more. But a Kolmogorov-Smirnov test we would call exact because we don't have to make any assumptions. We can just blindly apply it so long as we're testing the right thing, so long as we're testing the kind of the difference between two distributions. So parametric and non-exact tests are the ones that you need to definitely make sure that your assumptions are met. And so that's another reason why you are now armed with things like QQ plots, normality tests. I mentioned the Shapiro-Wilk test. That's an extremely high power test for normality. It has high statistical power. So with small amounts of data, you can trust it if it doesn't reject the normality hypothesis. And but follow it up with a QQ plot to be absolutely sure. So if your QQ plot looks normal and the Shapiro-Wilk also looks normal, you can probably move forward with your ANOVA or your t-test safely. And then for things like the chi-squared, checking to make sure that your assumptions like the expected number is greater than 5, that's important to do as well. Okay, so before I move on, any questions about that, about what I mean by parametric, non-parametric, making sure your assumptions are met, etc. Again, I'm hoping most of this is review, and where it is, I'm just trying to hammer it home, and where it isn't, I'm trying to open your eyes to these potential issues so that you don't run into them in the future. Okay. All right, so then we also talked last time about the chi-squared test and how it fits in to this general description of all hypothesis tests. And so kind of a graphical summary of the chi-squared test rationale without going through all the mathematical details. You've got here a single class, a single bin that we're worried about here. And you can say that if I've got 100 samples, and there is a 5.5% chance of those samples coming up in the class, like coming up in the bin, then I would expect on average to get 5.5 of those 100 in the bin. But I would actually get a binomial distribution of numbers of counts that actually land in the bin. So sometimes when I draw 100 samples, I only get 1 in the bin. Sometimes when I draw 100 samples, I get 12 in the bin. but I pretty much never get 20 in the bin, 25 in the bin, or anything higher than that. So these are the distribution of counts that would fall in a particular bin that only has a 5.5% chance of catching any of these samples. So that's the exact test, the binomial test right there. Now, you can say, well, at what point can I approximate a binomial as a normal distribution instead? And so what I've done here is I've plotted binomials and normals on top of each other. And these all have 100 samples for each one of these cases, but I've changed basically the probability so that the product N times P, the number of samples times the probability of landing in the bin, is represented here in the titles. And so as you can see, if my number of samples times probability is equal to 1, then I get the normal sort of fits over top of here, but you can see that a bunch of the normal comes up in negative outcomes. And so in the binomial distribution, you shouldn't get any negative outcomes. So this normal distribution, because so much is in the negatives, is a bad approximation. Similarly, if I do N times P equal to 2, so I've increased the probability a little bit, still a lot of the normal is over here. And you can see that it just doesn't quite line up quite well. We play this game for more and more and more, and it's not until we get this average value of 5, where the number of samples times the probability is equal to 5, that really it starts looking like the normal distribution kind of covers the binomial distribution perfectly. And so once you're up at 6, then it fits really well. And so the chi-squared test is a test that the math in building the chi-squared test is built on the assumption of normality. But the problem it's solving is a discrete problem, which really belongs in not to the world of the normal, but to the world of the binomial. And so what they did with the chi-squared test is they said, well, as long as NP is 5 or greater, we can replace the binomial distribution with the normal distribution. And that makes the math go much, much better. And so that's what's going on here. And that's the reason why your expected number of counts has to be 5 or greater. So we view the standard normal in the case of the chi-squared test as the kind of statistical distribution of how much variance in count we are allowing for each bin. So we're saying that under the null hypothesis, we would normally expect no difference from the expected number of counts in that bin. But if we're being fair, we're going to get some differences even under the null. And so, but how many differences are we allowing? So per bin, what the standard normal is telling us is we're really allowing 1, 2, maybe maybe we'll allow 3 differences away, but not really much more than that. So that's kind of what we're saying by modeling the normal. The standard normal is the null expectation for the distribution we land in each bin of all the bins of the chi-squared. And then it turns out that if you take all those differences and square them and sum them together, then that distribution is very easy to write out. It's another one of these like pivotal distributions. And for the number of bins you have, one less than that, that's the number of degrees of freedom. Because if you know the number of samples and you know the number of bins, once you have all but the last bin, you know how many have to be left over in that last bin. So if I have 10 bins, I have 9 degrees of freedom. 8 bins, I have 7 degrees of freedom. If you know the numbers of degrees of freedom and you view each one of those as a standard normal, and you square those standard normals and add them up together, then you can come up with a hypothetical distribution of the accumulation of those errors. And that's what the chi-squared the chi-squared is here. So you see with a degree of freedom, the yellow line here of 1, that's 2 bins, which means that really it's really only 1 real bin, because the second bin's number is kind of fixed by the first. Once I know the first, I know the second. So it's only 1 degree of freedom. And for that, I get this thing that peaks close to 0 and then falls off very rapidly. Well, that makes sense. If we only have 1 bin and are under the null hypothesis, if a standard normal is kind of what we're expecting is what we're allowing, then what this is saying here is that we're not going to allow much more than 1 unit of difference, 1 standardized unit of difference away when we add all of the bins together, because there's only really 1 bin that we're focusing on. But as you get more and more bins, then that difference, so what you're accumulating, you get a difference from expectation in one bin, a difference expectation from the other bin, and so on and so forth. And you accumulate all those squared differences. And then what that does to you is your null expectation of how much of a difference you're going to see is going to also go up. And so that's what we're seeing here as we go to 10 bins or 9 degrees of freedom, we get an average value that's closer to 8 or 9, because that is, again, the standardized differences are just adding up. And so if I were to plot instead the chi-squared on the value, statistical value on the x-axis, and the corresponding p-value on the y-axis, then if I were to pick a chi-squared value, let's say of 4, then the degrees of freedom basically gives me my tolerance for an error of 4, a chi-squared error of 4. So if I only have a 1 degree of freedom, which is 2 bins, then I am not allowing, that is a very, very low p-value. I am rejecting that hypothesis. But as I increase my degrees of freedom, so if I go up to 6 bins or 5 degrees of freedom, then that same value of 4 has got a p-value which is way above my statistical threshold of 0.05, which basically means that the more bins I have, the more error I'm just naturally going to accumulate, so I have to move the threshold up. And so that's all that we're seeing here. So that's kind of a summary of what's going on with the chi-squared. If you want to see a more concrete example, then what I've done here is I have created a hypothetical distribution across 30 classes, so 29 degrees of freedom. And so I just created a, I just picked, I'm going to say, well, I'm going to say on average, I'll get 6 here, 2 here, 4 here. I just created one of those. And then I drew data from alternative hypotheses, one represented by the blue distribution and the other represented by the orange distribution. And from those two alternative distributions across those 30 classes, I calculated the chi-squared value, and then I took histograms of that. And as you can see that as my alternative hypothesis gets closer in distribution to my null hypothesis, the histogram gets closer to the chi-squared distribution for that many degrees of freedom. That's what we're seeing here. So the blue one is the one that's pretty close. And the orange one, that is for a totally different, like a very different distribution across those 30 bins. I calculated a bunch of chi-squared values for it and took their histograms, and you can see that they're far away from that. So that is forming that same picture of the, which I think I've got down here. Well, that is forming the same picture where we've got our null hypothesis and our alternative hypothesis. And the alternative hypothesis gets farther away, it's more likely to reject. And if it gets closer, there's more ambiguity, you make more error. So that's kind of what's going on there. So that's the summary of what's going on with the chi-squared. So any questions about the chi-squared and the rationale behind the chi-squared? Is that pretty clear? And so, of course, you can't do this for every single statistical test, but I want you to at least feel confident that you could, in principle, go and understand the foundations of any statistical test you find yourself using over and over and over again. And so, things get more exciting with some of the other tests we've looked at. So, and so this is, I guess I meant so things get more exciting when it comes like Kolmogorov-Smirnov tests and so on and so forth. But even those, there is explanations for where these critical values come from. The only other things I want to mention about the chi-squared test, when you be careful of using it, is that there are alternatives to the chi-squared test that you should use in certain cases. So I mentioned that if you have very little data, the chi-squared test doesn't usually meet this continuity assumption. There are corrections for continuity that you can look up that people have used over time, but they're generally referred to being kind of poor performing. So instead, if you might find in more advanced statistical tools, they will have other things available like a G-test. So if you ever see the term G-test, think of it as a kind of modified version of a chi-squared test. It's sort of a chi-squared 2.0. A G-test is meant to be a substitute for the chi-squared that has weaker requirements. And so maybe you don't need quite as many expected in each bin. You also, whenever possible, you can try to use exact tests. I mentioned the binomial test. There's also the Fisher's exact test. And so if you read through statistical results, sometimes you'll see something that looks like somebody could have used a chi-squared, and instead they used a Fisher's exact test. And that probably is because they had very little data. So the Fisher's exact test is, any exact test. Those are the ones that whenever you have very little data, you should be Googling what is the exact version of a chi-squared test, and then you'll see, okay, it's Fisher's exact test. How does that work? You put your data into there, and maybe that's a more respectable test for your particular case. Then, we've already mentioned that, and so those are for tests of independence. And so that's the other thing I should mention is that when we use chi-squared tests, we use them for two things. We either use them to see if there's a difference between two populations, or there's goodness of fit, so an agreement. So we're either looking for agreement or we're looking for difference. When you're looking for difference between two populations, so as an example, you could say, well, what's the distribution of how much do people like, you've got menu items on a fast food chain, restaurant chain, and you want to say, do Americans prefer these menu items differently than, say, people in Great Britain? And so your treatment there is what country they're from. And then the distribution of counts across the menu items is what you might be testing. And under the null hypothesis, those two distributions would be the same. And then so you're testing to see if there's a difference in those. Well, you can use a chi-squared test of independence to see if there's a difference between those. And that would just sort of say, does country generate a difference between these distributions? And if it comes out and it says the two distributions are the same across the US and Great Britain, then you can maybe conclude that people go to this fast food chain in the same way, regardless of where if they're Brits or they're Yankees. Goodness of fit is the other way around, where you're not looking for differences, you're looking for similarities. And so you're saying, I think these data are exponentially distributed. I want to test the goodness of fit of the exponential to these data. And so the chi-squared is one way to do that. We've also already learned the Ks test is an exact test. So that means that it's probably going to be good to use with low amounts of data because it has higher statistical power. And if you're interested, I go into details about how the Ks test is derived. It has to do with something called a Brownian bridge. I love talking about this stuff, but I generally detect that students hate when I talk about this stuff. So I'm going to skip over it. But if you're interested, let me know, and I'd be happy to tell you how the Ks test works. But for now, just know there is a method to the madness. And then the other tests that you'll see pop up in your statistical tools are an Anderson-Darling test. It's another great test for goodness of fit because it is high statistical power. So it's not so great for testing independence because its high statistical power makes it a little too touchy, too sensitive, but it's a great test for goodness of fit because it's so sensitive. And then the one that I do want you to remember is the Shapiro-Wilk test, where if you need to test for normality, which you often need to do before you go and do a t-test or an ANOVA, you need something like the Shapiro-Wilk test, which is an extremely high statistical power test that is customized for just testing normality. So that's why if you need to know if something's normal, go to the Shapiro-Wilk test, and then usually couple that with a QQ plot before you run into your t-tests and your ANOVAs and such. Okay, so any questions on that? The basic, I'm trying to build in your head a taxonomy of tests. Is that, because when you go and you start working with data, someone's not going to be sitting there and saying, apply a t-test, apply a chi-squared. In your head, I want you to start building a decision tree where you say, for these types of data, these are the tests available for me. For this question, I'm asking, I need to do this test. For this other question, I need to do this test, and so on. So that's what you should be kind of building up over time. So any questions, comments, concerns? Okay. All right, so we're almost done with the review here. So this is something that I didn't quite get into as much in the last lecture, but I did at least want to highlight something from the slides that I kind of jumped over in the last lecture, this so-called phishing problem. This is a common statistical setup for your simulations. You got a sim model that you built. You're going to measure multiple things coming out. You've got random variables coming in. These are your input models. And you've got decision variables that you've configured, probably fixed, they're static. And so you would like to see, is there a difference? So given I've got a certain set of input variables or input models coming in, I might decide I want to see, is there a difference between using one teller and two teller? Or maybe be using two tellers in one line versus you know, so many tellers and so many other lines. Or you know, what's better, me doubling my tellers or me increasing training so that each teller is faster? You could, there's a bunch of different things where you want to test multiple treatments and look for differences. But the problem is you have lots of things that you can measure and look for differences from. So coming out of your simulation, you could look at utilization, you could look at delay, you could look at maximum line length. And then the question is, what happens when you detect a difference in one but not the other? Or how does the existence of even looking for differences in multiple things affect how skeptical you should be when you find a difference in one? This is the so-called Phishing problem, is that if you have lots and lots of things to measure, if you know, you have these two things, like you say, well, I think that apples, you know, have a difference in your physiology. Like people eat apples versus not eating apples. You can say, okay, well, what do you mean by difference in physiology? And then you start doing all sorts of tests. Well, we're going to see how far they can run without running out of breath. We're going to sample their blood and look for a bunch of different analytes. We're going to maybe put them through cognitive tests. Eventually, you're going to find a test where your two populations, apple eaters and non-apple eaters, have a difference. But you have to keep in mind that every single one of your tests has a type 1 error. It will detect a false difference 5% of the time. And if you combine tests over and over and over again as a kind of super test to find a difference between apple eaters and non-apple eaters, then all of those type 1 errors almost have an additive effect to each other. So this is the phishing problem, is that if you go fishing, eventually you're going to catch a fish. And so the question is, you know, if you find a difference, what does that allow you to conclude about the change in your decision variables? And so that's the motivation here. And it suggests that if you're measuring multiple things, you somehow need to adjust the false positive rate on each individual thing. Because if it's all 5%, if there's a 5% chance of getting a false error, a false difference in utilization, and there's a 5% error of getting a false in delay and a 5% error in line length, then the probability of detecting a difference in the whole simulation is going to be much greater than 5%, and that's the big problem. And so that I've sort of summarized mathematically on this slide here, where I'm saying the probability of at least one false positive, we can model that, and that's just 1 minus the probability of no false positives across all the variables that you're measuring, which is just 1 minus this, because each one of these outputs we assume to be independent, and which is definitely, this number here is definitely far greater than your desired type 1 error. So for this reason right here, the false positive rate across the family, we refer to this as the family-wise error rate, is always going to be higher than the false positive rate for any independent individual response variable. So the simple way to deal with this problem is, if you're using a family of response variables to detect a difference in your simulations, you don't want to use alpha equal to 0.05 for each one of your variables. Instead, you want to do alpha divided by the number of comparisons that you do. So if I go back here and I say, I'm going to look at 3 different variables, and I'm going to look for a difference in this variable, and this variable, all separately. Those are 3 comparisons. So that suggests that for each one of those tests, I need to use alpha divided by 3. So instead of using 0.05, I do 0.05 divided by 3, and that gives me 0.017. So, or 0.016 to be safe. So in order for me to get a 5% family error rate, I need a 1.6% individual test error rate because I'm doing multiple tests. Okay, I want to let that sink in. That if you're measuring multiple things out of your sim and you're doing a t-test, then you need to make sure you adjust your error rate so that the family error rate is 5%. And that may mean making the individual error rates much smaller than 5%. And we'll see that again as we move on and talk about relative error in some future lectures. This is the standard kind of, if you got nothing else to do, you do this so-called Bonferroni correction that I just talked about. In reality, when you have access to more sophisticated statistical tools than we cover in this class, there are even better things to do. Like you can do, there's a multivariate ANOVA, where you can measure differences across multiple response variables simultaneously. There's also things like, this is for a slightly different problem, an ANOVA with a post-hoc test. And so that's the case where you've detected that there's a difference in, you know, if you've got 5 countries and you're measuring how each country does something, and you might detect that there is an effect of country, but then you want to detect how to rank these countries. Well, that is another comparison problem, because then you're going to compare the response variables from country A, the response variables from country B, the response variables from country C, and then eventually rank those countries A, B, and C in terms of their average response. Well, you can use the Bonferroni correction to deal with that multiple comparisons problem, where you might have a lot more comparisons because of all the combinatorics. Or you can use what's called a post-hoc test. So you can run what's an ANOVA, which you've already learned about in 380, and that'll tell you there's a difference in between countries. But then when you rank those response variables, you run then something called a Tukey test, or a lot of engineers like to use Fischer's LSD. And so these 2 tests then will do the ranking for you in one shot, so that you don't have to do all these individual tests, and so you don't have to compromise on your type 1 error. So these tests are going to have much more statistical power than this test. So so remember, there's a trade-off between statistical power and type 1 error. If I reduce my type 1 error, I am going to increase my my type 2 error. And so that's the downside of the Bonferroni correction. You're making your type 1 error so small that you're amplifying your type 2 error and killing your statistical power. All right. So I mentioned that engineers like to use Fischer's LSD and not a Tukey test, and that's partly because Fischer's LSD might be, it has it compromises on type 1 error, because engineers are actually more okay with finding differences when they're not there, because they can exploit those for speculative R&D ventures. Whereas in science, you've got a data set, you've got one shot to detect it if there is a difference. Does the COVID vaccine work? You better get that right, you know, because you put a lot of money into that study, and you're not going to dump a lot more money into that study. And so effectively the next study is distributing the COVID-19 vaccine. So you better get it right in your scientific study. That's why in pharmaceutical trials, you might have a type 1 error rate that's really, really small. But engineers, we amplify our type 1 error rate because we are speculators. We do want to look for those potential differences because we are going to follow up with more stuff after. And that's the reason why engineers use a Fischer's and not a Tukey and a bunch of other things like that. So that was the last thing I kind of covered last time. So that's all the review of all the stuff that I hoped we had covered by now. So before we cover a couple of new things, are there any questions about any of that? This class is meant to make stats something that is practical and useful and less abstract. And so that's what I'm just trying to build up in you, is a feeling that stats are a tool that you can apply to lots and lots of things, and you should feel comfortable with them. But you have to realize stats is not a single hypothesis test. It's learning how to use a family of hypothesis tests together to solve a problem. And that's really what industrial engineering is, after all. It's solving these problems. All right. So we moved on to a new unit, and those of you who started reading the book have seen kind of where we're going with this. So we are focused on kind of a discussion like the one I was just talking about here. What do we choose to measure, and how do we make inferences on those things that we measure? And how do we decide how many simulations to run to achieve a certain amount of statistical power? And how do we then decide per simulation run, how do we adjust the simulation so that we can reduce the time it takes to finish these simulations? Because simulations take time themselves, very complex simulations. So it's generally, we're getting into the point of deciding what to measure and how to alter our simulations to measure them more efficiently. And that requires breaking up our systems into two types, a terminating and a non-terminating, which affect the way in which we decide how long and where we start and where we end basically our simulations. So these two types of systems each correspond to two types of simulations. So there's transient simulations and steady state simulations. Very often people just swap these words, terminating for transient and then non-terminating for steady state. I'm happy with that. If you want to swap those terms, that's fine with me. But just strictly speaking, terminating and non-terminating are the systems, and transient and steady state are the simulations, the models. So what are these things? So if you've already read in your book, a terminating system, it naturally terminates. It runs either until a stopping time that is natural for the system, or it runs until a certain condition is met. So the end time could be fixed ahead of time. So we know the bank is only open from 8 to 5. It ends at 5. The doors lock at 5. It does not go over 5. Or maybe it's a little more gracious bank and they end when the last customer is handled, or 5 o'clock, whichever one kind of comes last. And so in that case, the condition that is met is when the queue in the bank is 0. When that queue goes to 0, then the bank closes. And so that could be a condition, but either way, we imagine the bank closing at some point. It doesn't run forever. So we simulate a terminating simulation, or a terminating system, by a transient simulation. We use the word transient because we actually care about all of the things that happen when you turn the system on, which is sort of a flip side of saying we care about the fact that systems can be turned off. So a bank opens in the day. Well, initially there might not be people in the bank, and so it's going to take a while for people to flood into the bank. We care about that time it takes for people to enter the bank and set the bank up. We care about the transients. We care about the time before the bank kind of settles out into its steady state. Because we care about the transients, we refer to this as a transient simulation. The simulation is modeling the transients. The transients matter. So that's kind of the example that I'm getting out here. And inside Arena, you've seen that under the run setup, that we've got these conditions here where there's a terminating condition. So you either can end at a particular time. So notice under replication length, you can set this for a finite time, which is what you've done so far. But in like the call center module, or the call center example, then if you look at its run setup, then down here, the terminating condition says, either we've reached 600 minutes, or whatever this is, or hours, whatever the units are, your hours, base time units, minutes. So either we've reached 600 minutes, or the terminating condition is we have reached 600 minutes, and the number that are waiting in the trunk line is equal to 0. So there's nobody on hold. So that's an example where the end time of the call center will be variable, but there is an end time. People do go home. The call center does not run 24/7. So that's what I mean. It is a terminating system, the call center, and is a transient simulation because we're capturing the way the call center starts and the way it ends. We contrast with that with a non-terminating system. A non-terminating system is one where we only are focused on its long-run behaviors. So these are systems that very often we view as ideally running 24/7. So our simulation has to start, but so our simulation is going to have some ramp up as it kind of it starts filling its queues, and so it has transients. But the transients in our simulations we discard. because they are artificial, because in the real system, there are no transients, because the real system we view as being continually running for all time. It goes to negative infinity in backward time and positive infinity in forward time. So it runs for all time, and we're only capturing the average in the steady state. So we don't focus on those ramp ups. But when we hit run in Arena, there is a ramp up. It's just going to happen. And so we'll have to discard that. So the properties are not influenced by the initial conditions in the real system. So we are going to need to adjust our data that we gather from our simulation so that our simulation data also is agnostic to the initial conditions. And so you can either do that by picking your initial conditions carefully. So like in an inventory management system, what is your initial inventory? It's probably not initially 0 because there's going to be some ramp up as you're waiting for that first order to come in. So maybe you set your initial inventory to the average inventory in the real system, and that way there's less of a ramp up in your simulated system. Or you set the stopping time late enough that you have plenty of time for that initial transient to occur, and then the system to then still have plenty of time to run for long enough for you to get a good average of the steady state behavior. And then you can just discard all of that transient stuff that you did ahead of time. So that's going to be our two sort of levers in these types of simulations, is how we set our initial conditions and then how long we run the simulations. And then implicit in there is how much data do we discard from the front of those. And examples are 24-hour grocery stores, for example. If you're simulating a 24/7 Walmart, your simulated Walmart is going to ramp up in its starting, but the data you actually care about is the kind of long run behavior of your simulation. You don't care about that ramp up because you're simulating a Walmart that doesn't ever close and open. So you're simulating, you're trying to build a sim that's capturing that Walmart as it runs continuously. And so this is just a depiction of everything that I've kind of said already. In the terminating systems with the transient simulations, you care about everything, the ramp up and the stop. So all of this are good data. But in the non-terminating simulation over here, even though that might be the same simulation logic, so I get the same trace of data out, the initial period here is an artificial thing that just happens in the simulation. It doesn't happen in the real system. So these data here, I have to throw away. I have to truncate this, because if I include it, it's going to bias my steady state estimate. The real steady state estimate is going across here. So the real steady state estimate is, if I can find my annotation here. The real steady state estimate is around here, but if you include these data here, you get a steady state estimate down here, and that introduces what we refer to as bias. So to get rid of that bias, you get rid of these data and you only consider these data, and that will move your estimate up to the proper steady state. So that's what we do in the so-called steady state simulations of non-terminating systems. Okay, questions about that? Is that clear what we mean by these terms? Okay. So I normally would do an attendance exercise where I'd ask you to sort of practice this. So just kind of think of it in your head. Again, we're not doing attendance exercise today because of it's being election day. But I will kind of start kind of a little intro to an example here where giving you an example of the, oh, sorry for that scroll wheel issue. Where in this example that is borrowed kind of from the book here, this is an example of for the different types of variation that you'll get and the issues that you get both in that separate transient simulations from steady state simulations. So I've got a simulation that runs for say 5,000 minutes. And I run that simulation and I can run it 3 different times. So that's what I've got down here, 3 different times here for these simulations here. Now, if I'd like, I can take those 5,000 minutes and I can cut them up into 5 groups. So 0 to 1,000, 1,000, 2,000, so on. So right here, I've got these statistics that I can calculate within a replication, and I've got statistics that I can calculate across a replication. So what this is showing here is that you can get variability in those statistics in both directions. And so within a replication, so here's one replication here, then I can see that in the first 1,000 seconds, if I take an average, then you know, this average looks actually kind of similar to all the other averages here. So there's not a lot of variability here, but when I rerun that simulation a second time with a different random number seed, then I end up seeing at least what looks to be a significant difference within the simulation. So early in the simulation, the numbers look a lot lower than later in the simulation. And then for a totally different random number seed, then I get a very different pattern where suddenly the numbers go back down again. And so you can get variation within a simulation that we have to consider, but that variation within a simulation might still be correlated to the particular circumstances of that sim. So this particular random number seed didn't see any of the patterns we see across these random number seeds. And so even though you might view these as replications, I can't view these as independent replications. Clearly, I cannot generalize from replication 1 to replication 2 and replication 2 to replication 3. These are just 3 different beasts. Even though it's the same simulation model, putting in 3 different seeds gave me 3 different patterns out. So then I could then take an average across all of those 5,000, and then these 3 numbers are independent from each other, and just shows that across 3 different seeds, so across replications, even though here I had some individual times that were larger, the average across all times is very similar to the first random number seed. But in the third one here, even though these numbers look kind of similar to these numbers, the average across all time is significantly higher. So we can see there's lots of different sources of variation here that we have to deal with and be careful about. And the whole question is, how best can we generalize from our simulation to our real system, or from a couple replications of our simulation to many replications of the simulation? So I'm using terms like replication and all that, so we're going to try to start defining those. So if we've got independent observations, which we normally get from using separate random number seeds, then every time I take data from a sim, I get a set of data points. And so now I'm referring to down here, these 3 numbers at the bottom here. If I want to take an average of these 3 numbers, I can define the standard error of that mean. And the standard error of the mean, the SEM, really can only be defined when you know your samples are independently drawn. So it's not really legal for me to take a standard error of the mean for these numbers inside the replication, because this number is not necessarily independent of this number. So you know, knowing that this number is low might tell me something about this number also being low. So I really can't average all of these things up together and then generate a standard error of the mean here, because the formula for standard error of the mean assumes that each one of these numbers is independently drawn. But I can do that across replications. This number is independent of this number because they use different random number seeds. This number is independent from this number, again, different random number seeds. So I can do a standard error of the mean across these numbers. So that's what I mean by when you can use the standard error of the mean. But that characterizes the variance in your mean estimate, the standard error of the mean. So for these cases where things are independent, we often, so how do we guarantee independence? Well, we generally do that by running a fresh simulation run, and that helps guarantee independence. And running a simulation run with a new random number seed is how we guarantee that one simulation's numbers are going to be different than another's. And in that case, I'm going to use the term replication. I've already used this a couple of times. A replication means that we have an independent sample of a process, and we ensure independence with different random number seeds in simulation. Across replication data are independent, and in the case of simulations, identically distributed because we use the same sim to generate them. And in the case of simulations, very often they are normally distributed because of central limiting effects because a lot of times the data we gather from a giant simulation is an accumulation of data from within that simulation. And so because of that, the central limit theorem suggests that the average that we get out of these simulations will be normally distributed. And so that's what makes across replication data so well suited for t-tests and ANOVAs, because they very often will be independent and normally distributed. And that's the reason why I generally don't worry about you doing a Shapiro-Wilks class test in this class, because this class's data usually fit the assumptions of a t-test or an ANOVA. All right, well, I feel like that's a good place for me to stop, and we can pick up with that next time. So I guess I don't have an attendance question for you. So if you have any questions, I'm happy to take those. Otherwise, I will see you Thursday. And if you have an opportunity to vote, go ahead and give it a shot.
Hey, Professor, I have another question.
Uh-huh.
Your slide that shows the terminating and the non-terminating, I was just wondering, that looks almost like kind of a first order response to maybe a unit step function or something like that. Would it ever make sense to, like, I don't know, generate like a transfer? Do we ever do that? Would we ever like generate like a transfer function for something like this and try to estimate parameters for that? Or is that something that is just kind of not, I did circuits and I did a Bodie plot, and it looks very similar to that. I was just wondering if that's something that industrial engineers.
Well, sure. I mean, kind of the dirty little trick about undergraduate education and engineering is we're actually just teaching everybody to be engineers, but it's hard to convince people to. But we have to come up with curriculum to make it more palatable. And so, absolutely, learning about step responses, and I mean, so I would call this like this isn't a first order because it's rings, and so this would be a at least a second order response because it's got these kind of like oscillations that are coming up here. And I think it's an excellent connection you've made there. I mean, effectively, what you do when you do what we refer to as system identification, when you take data that has a ringing like this, what you're saying is that I can model that with a differential equation. That's what a first order response is, or a second order differential equation. That's two differential equations together. That's a second order response, which will give you this kind of ringing here, which means that I can take a system, a physical system out there, and reduce it into something much simpler. And in fact, in systems theory, we refer to this initial part as the transients. And so I guess the reason you use a simulation is that we're saying that what if your system is like if you're ringing a bell, and you're looking at the oscillations of the bell as it's ringing, it might be good enough to just use two differential equations to simulate that. But if you're talking about a bank, you can still get this kind of rising and oscillations here. But when you actually try to fit a first order exponential or a second order response to it, it just doesn't quite fit that well. And so simulations are an alternative way to model those data. And I guess you'd say the electrical engineers, when they generate a step response, they care about the transients very often, because if you're building a cruise controller for a car, you care about how much it overshoots the set point and how much it shakes around the set point. You really want the cruise control of the car to hit the set point and stop there. So you want it to be critically damped. You don't want it to be under damped, and you probably don't want it to be over damped either. In our case, we're saying we have systems that we can't quite go so far to approximate them with that level of mathematics, but we still care exactly about the transients. So we really want to make sure that when people rush into the bank, we don't get a flood of extremely long lines followed by these boom and bust cycles. And so So we are interested in exactly the same things that an electrical engineer is interested in when they're designing a feedback circuit. But we just happen to be working with systems that are often not well modeled by second order differential equations. So I think it's an excellent connection, and I definitely think the connection's there. And industrial engineers definitely care about those things, but the industrial systems we work with are often complex enough that we can't use those simpler models. But if we can, absolutely, industrial engineers will use those simpler models.
Gotcha. Okay, and as far as I can see, you're saying Thursday at 4 would be a good time to meet.
That's my normal office hour, especially this week with PhD defenses. It's hard to schedule things. So if you can meet then, that's great.
Okay, I'll relay that to the group. Thank you.
Okay, good. Bye.